back to the session, right. So, in the previous session we discussed about the properties of first order system, right. We had seen what are the basic first order system and we had seen the example of first order system, right. It means whenever we use the feedback element just like the sensors and you can say the basic encoders. So, that will be under category of first order system. So, last time we were discussing about the time you can say the response of the first order system. It means if we apply our test input to the first order system, then what would be their response. So, in today's session we will discuss in detail about the step response, ramp response and parabolic response of first order system, and then we will look about the second order system, right. After that we will look about the response of second order system in detail. Okay. So, last time we had seen this impulse response, right. So, where our R s was acting as input quantity, okay, and here Y s was coming as the output. So, for impulse my R s was 1 and this was the response coming, okay. And if we see this Y t response in time domain is given by this term, right. It means if I put here t equal to 0, you can see this is the time domain analysis. So, this is the time axis in the x axis, you can see this is t. So, this is t equal to 0. Now, we are varying t equal to t, 2 t, 3 t, 4 t, right. So, here in this expression if I put t equal to 0, so I will get here y t equal to 1 over t. So, that is why my initial point is here this 1 over t, and as time t tends to infinity, then this y t will be equal to 0, because this exponential term if I keep here t equal to infinity. So, minus infinity will leads to the 0. So, this time response we had discussed in the last session, right. So, now second step response, okay. It means if I am having a first order system and I am providing here a step signal in the input, right. So, what would be my output response, okay. So, this is my desired input and I want to make my output should behave like this. So, I can say this may be my desired output also, okay. So, what would be the actual output will come, we will see after this analysis. So, this is my y s, same transfer function will remain for first order. Here R s will change for step input, R s is 1 over s, it is given as 1 over s tau s plus 1. If you solve it using partial fraction, you will get this expression. If I take the Laplace inverse, this will gives me 1 and this will gives me exponential of minus t over tau, right. So, this is the my output response, okay. So, what would be this graph, okay. So, here there would be a exponential decaying graph, but subtract by value 1. So, this is happening in minus direction. So, if you perform this, so you will get a graph like this. So, here I provide my input, you can say this graph, this is my step input, okay, and you can say this is my desired output also, right. And the response, you can say this is the exponential behavior that you are getting here, this is my actual output. This is my actual output. So, here this is happening. So, in this case if I see what is the transient present here, this transient is this exponential term. So, this exponential term is basically the transient present in this graph, and if I would like to see what is my steady state value, this value is here 1, right. So, basically our time response consists of transient response and steady state response, right. So, this is the basic graph. So, here what we are doing, so we are keeping here first tau equal to t, okay, capital T. So, here if I make this exponential of minus t over capital tau, you can say if I make here t equal to capital T, this will become exponential of minus 1 and it will become approximate 0.63. In percentage it is 63.2%. In the same way when I make here 2 t, so this will become exponential of minus 2 capital T over t, it will cancel out if I see the value of exponential minus 2, it will come 0.86 something, and if I take it percentage, this will gives me 86.5%. In the same way for 3t, I will obtain this value, for 4t, I will obtain this value, for 5t, I will obtain this value, and if I plot, so I will get this response, and this response is basically the actual response coming from the system. Okay. So, this is the step response. In the same way for ramp response, I have to select my ramp signal R t equal to t, where R s is given as 1 over s square. Okay. This is the S domain, Laplace domain, right. So, again I have to use same transfer function, only R s will change. Now, I am getting this transfer function. So, with the help of partial fraction, I will obtain this expression. Now, this is available in S domain. What is my aim? I have to obtain my output response with respect to time, that is y t. So, here y t equal to, you can say Laplace inverse of y of s, and this will gives me this expression, because 1 over s square is here, replaced by t, tau over s replaced by given by tau, because 1 over s is 1, and this term if you take the Laplace inverse, you will get this term. Okay. So, now if I look for the total analysis, so what would be here transient? So, I need to look for exponential term. This term will gives me the transient, and remaining term will gives me the steady state response. Okay. So, here you can say the steady state response would be t minus tau, and transient term would be exponential term. So, when I plot this, so you can see this is my ramp signal that I am providing the input. Okay. And then I am providing, after getting this input, the system response is going like this, and it will goes to the infinity. So, there is a gap, you can say this one is the actual output. So, now there is a gap between actual and input signal. So, this gap is basically the steady state error. So, what is the steady state error? We will discuss in the upcoming slides. Okay. So, we will see in detail what would be steady state error for unit step, for ramp signal, for parabolic, we will see later about it. Okay. So, in the same way we are keep varying this time as 2t, 4t, 6t, and this graph is obtained. Okay. This is the ramp response for first order system. Now, we will go for the parabolic response, where we have to apply this parabolic input. So, if I take a Laplace transform of this, I will get 1 over s cube. Okay. So, same transfer function I have to use, then R s equal to this much. Then if I use the partial fraction, it can be written like this. Now, I am interested in output in time domain, I have to take Laplace inverse of y of s, then I will get this expression. Okay. So, here 1 over s cube is here, t square by 2, tau over s square, tau of t, 1 over s will be 1. Okay. So, this type of Laplace inverse we had taken in the previous slide also. So, again we need to separate out what is the transient and what is the steady state. In that case, we have to look for exponential term again, right. So, this exponential term will be our transient analysis, and remaining term will become our steady state analysis. So, here we are doing this experiment, doing this graph for different value of tau. So, here I am putting 1 tau equal to 1. So, I am getting this blue graph. Okay. In the same way, whenever I am putting tau equal to 2, so I am getting this graph. Okay. So, this is my, you can see the red line, this is my input, and these two response is my output, or you can say actual output. So, this is my desired output and this is my actual output, and the difference between them will be steady state error. Okay. So, here what is happening if I keep increasing tau value. So, the steady state error, or you can say difference between input and actual output is keep increasing if I increase the value of tau here. If I further increase value of tau, this gap will increase, you can say the gap between input and actual output, right. So, this will happen for the parabolic response for first order system. Now, we are coming for second order system. Okay. So, what are the second order system? We will see in detail. Okay. So, we can say a system basically having the two poles, they are called the second order system, right. So, how to obtain the order? For that purpose, we have to obtain the closed loop transfer function, then we need to write 1 plus Gs Hs expression. The denominator term of that transfer function will be the, you can say, the equation, quadratic equation, and the highest order of S will gives you the order of equation. So, this thing we have done earlier. Okay. So, the response of second order system or higher order system, it exhibit the continuous and sustained oscillation about steady state value. So, whenever we discussing about the second order system, so we will get the oscillations at the output. So, till now we had discussed the response of first order system. So, you can see in every graph there is no oscillation, right. So, whenever we are dealing with the second order system, then we will get certain oscillations at the output, okay. And that oscillation will have certain frequency, and that frequency will be the natural frequency, that is omega n. So, omega n will be the natural frequency of response, it will come at the output whenever we are dealing with the second order system. So, here is an example of a indicating instrument. This may be, you can say, compared with the PMMC, permanent moving coil system. Okay. So, basically it is a DC instrument, it will measure the DC quantity or DC current. So, what is happening, this is a needle, okay, and this is the spring type or spindle type of system present here. This is the magnetic field, the whatever current that I have to measure, it will flow across it, it will generate its own magnetic field, it will interact with the magnetic field already present here, and it will generate the torque, okay. And this torque will rotate this needle, and then we have to add here certain damping system which will oppose this torque and stop at certain value. For example, it is 2 ampere, so it will stop at 2 ampere. So, this system is a example of second order system, okay, where you are observing the movement of a mechanical thing just like a needle. So, this needle may have certain mass J, inertial mass, it is moving along, you can say, this axis, this is the angular displacement theta, okay, and we are applying here certain opposing torque, so that this needle will stop exactly at 2 ampere. So, you can say we are providing the damping or frictional part, you can say B would be here. So, if I like to model a system which is having a inertial mass J, having a opposition of B, having a displacement of theta, then we can see this type of equation can be explained like this. We have done this type of thing in unit 1. So, where torque is given by J d2 theta over dt square plus B d theta over dt plus k theta. So, this J is because of inertial mass, B we are opposing this torque present in the system, okay, and this k, which is because of the spring type of spindle type of system present in this indicating system. Okay. You can see this spring type system will gives you the spring constant k, right. So, if I take the Laplace transform of this, I will get this expression, and if I would like to write the transfer function output by input. So, my output is here angular displacement theta, input is here torque, and this would be my transfer function for it, okay. And I can rewrite if I take J common from denominator. So, this would be my transfer function. Okay. In the same way, if I consider here a electrical network basically consists of series RLC parameter, and we are applying here certain input and we are observing output across C. Okay. So, what would be the equation I would like to apply here KVL? It is having single loop, this expression will come, then it is already in S domain. So, this will be the expression, this will be given by SL and impedance across L, and impedance across C would be given by 1 over HC. So, if I solve it, I will get this type of expression, and my output would be like this, V equal to IR. So, I am measuring the output across the C. So, that is why this is my output equation. So, for transfer function, I need to take ratio of output quantity by input quantity, and I will get this expression. Now, I will take LC common, this will become my transfer function for electrical system, right. So, what is the common between this electrical and indicating type of system? So, here you can observe that this S square term is present here, S square is here, S term is here, it is R by L, S term, and here you can see it is B over J, and the constant term is 1 over L C and it is k over j. So, if I put here j equal to 1, b equal to 1, k equal to 1, then this will become 1 over s square plus s plus 1. Okay. In the same way, whenever I put here r equal to L equal to c equal to 1, then this transfer function will become 1 over s square plus s plus 1. So, here you can observe the transfer function for electrical and this indicating system is same if we evaluate their parameter equal to 1, right. So, this is the limitation of transfer function. If I am having this information, then I do not know for which system it is belonging, whether it is electrical or indicating, I do not know. Okay. And if I combine, if I would like to write the generalized equation for second order system, it would be written like this. So, here this is the output quantity y of s, r s is the input, the ratio is omega n square over this term s square plus 2 zeta omega n s plus omega n square, where omega n is the natural frequency of oscillation that we talked about in previous slide. It means, if we are dealing with the second order system and providing the test input, we will find out a certain oscillations in the output response. That oscillation will have certain frequency, that would be omega n. So, now new term is here zeta. Okay. So, we will discuss about zeta in the later slide. Okay. Zeta is basically here a damping coefficient or damping constant factor. So, if we look for the standard second order system, it would be given like this. So, this is the expression of open loop transfer function, and I would like to obtain the closed loop transfer function for it, right. Then y s over r s would be this expression. So, how to write this? You can say G s is given like this, okay, and I have to obtain the closed loop transfer function, that is, you can say CLTF is equal to G s over 1 plus G s H s. If I assume here the feedback is unity, so you can say it is G s over 1 plus G s. So, if we evaluate this expression, then we can reach from here to here. One alternate method is, if I am having the open loop transfer function, so CLTF can be written as numerator part n of s, denominator part would be d of s plus n of s. So, in a minimal calculation, we can obtain the closed loop transfer function here. So, you can check my G s is this much. Okay. So, I can write, if I am following this convention. So, my numerator is here omega n square, there is no s term is here. Okay. Now, my denominator is here this term s multiplied by s plus 2 zeta omega n, right, plus numerator I have to do, my numerator is omega n square, so plus omega n square. If I solve it, this will become omega n square over s square plus 2 zeta omega n s plus omega n square. So, how simply we calculate a transfer function, you can say closed loop transfer function from this open loop transfer function. So, here zeta is what, basically it is a system damping ratio. Okay. Again damping term is coming, it means it will oppose something. So, zeta factor here, it will oppose the oscillations present in the system. Okay. So, later we will see the definition of zeta term. Okay. So, here we would like to know what would be the poles of this second order system. Okay. For that purpose, we need to know, this is my equation of denominator, and this equation will give us the pole, right. So, if I factor this equation, then I will obtain the pole. So, my equation is here s square plus 2 zeta omega n s plus omega n square equal to 0. This is basically 1 plus G s H s, right, quadratic equation. So, if I find out the root of this equation, I will get the poles. Okay. So, for that purpose, I will use the formula. So, my s value would be, you can say minus b is here plus minus under root of b square minus 4 a c by 2. This is the equation. So, here I would like to replace this s equal to minus b. So, minus b is here 2 zeta omega n, okay, plus minus you will get here b square. So, 2 zeta omega n whole square minus 4 a c. So, it is 4 times of omega n square, divide by 2 a is 1. So, this will be 2. Further, if I solve it, this will gives me minus 2 zeta omega n plus minus. So, here I need to take out 4 omega n square. If I open it, this will be 4 times of zeta square omega n square. So, 4 omega n square present here, 4 omega n square present here. So, I need to take common 4 omega n square. So, basically I am taking common here 4 minus of 4 omega n square. So, if I bring out the minus term, so I will get here j term out of this square. Okay. So, this will be 4 omega n out of it. You can say it will be 2, because it whenever it come outside the root, this will become 2 omega n, okay. And in the under root, this will be zeta square, because I had taken the minus 1, this will become 1 minus zeta square, because I had taken the minus sign at the output, right. So, but that is why j term is coming here, divide by 2 a. So, 2 and 2 they will cancel out. So, you will get here minus of zeta omega n plus minus j omega n under root 1 minus zeta square. So, this is the basically the poles, or you can say root of this equation. So, if I plot it on the s plane, this is the imaginary axis, this is the real axis. So, on the real axis my value is minus zeta omega n, and in the imaginary axis it is omega n, right. This value is omega n under root 1 minus zeta square. So, if I plot it in the s plane, this would be the location of this pole, right. So, here we can see it is making angle theta here, right. So, if I like to know what is the cos theta. So, cos theta is basically you can say the base value is zeta omega n, and this is the hypotenuse, you can assume is here d, you can say you can assume here h, divide by h, okay. So, h can be calculated by previous formula, you can say this is the base square zeta square omega n square plus this distance, you can see this height is omega n under root 1 minus zeta square. So, it will become omega n square 1 minus zeta square, right. This is the h square basically. If you solve it, this is zeta square omega n square plus omega n square minus omega n square zeta square, this term will cancel out. So, h square is basically omega n square. So, if I take h, this will gives me omega n. So, it is positive quantity. So, I have to assume here positive root. So, zeta omega n by omega n. So, cos theta is here zeta. So, zeta is basically the damping coefficient, it is the ratio of you can say actual damping upon critical damping. Okay. So, critical damping will happen whenever zeta is equal to 1, and whenever zeta is not equal to 1, that would be the actual damping. Okay. This ratio is given by zeta, right. So, what about the sine factor here? So, sine theta would be given as this height is omega n over you can say under 1 minus zeta square divided by zeta omega n. This will cancel out and this will become the sine theta. So, in upcoming derivation we have to use this sine and cosine term. Okay. So, now we will look for here the basic system parameters. The one system damping ratio is here zeta, that we discussed, ratio of actual damping to critical, system natural frequency omega n, the frequency of oscillation, and one more term is here omega d, that is omega d equal to omega n under 1 minus zeta square. So, if you see here, this is the root. So, if I assume that this is a term omega d damping coefficient, then this root will become s equal to minus zeta omega n plus minus you can say j omega d. This is the basic root coming in this case. So, this is the omega d damped frequency. Okay. So, this is the angular frequency at which system tend to oscillate in presence of damping force. Okay. So, this is the basic introduction. Remaining term we will discuss in next lecture. So, thank you. So, remaining term we will see in the next lecture. Thank you for today.